Hello.
Hi.
Hi, can you hear me okay?
Yeah, it's really a honor to meet you.
Oh,
I'm in honor. Oops.
that's very kind of you. It's lovely to meet you too. How are you today?
Well, I'm fine.
Good. Okay, great. Good. So I've read your little introduction. It sounds amazing. I'm so glad that
Thanks.
you're deeply in love with physics and maths and biology.
My most
So
interested part is about quantum mechanics.
yeah, of course we can talk about that if you'd like.
Okay.
Yeah.
Uh, okay. Well, well, I, I want. You see, is time traveling possible?
I think that's a very, very difficult question. I think the answer at the moment has to be no, I would say, because think about it. In the future, if someone did invent time travel, well, say for example, I invented time travel,
Okay.
but say I only invented it when I was 60 years old.
Okay.
Well, what would I do at the age of 60 if I had just invented time travel? Well, I might go back in time and tell my younger self how to do it.
Yeah.
Right? And
Oh,
so if it exists in 60 years, then it should probably exist now.
you're right.
Yeah. So
You're right.
that's one idea, but maybe it's possible that in the future they invent time travel, but there's some rules of the universe that we don't understand yet that mean that they can't tell us how to use time travel now. But I mean, who knows? It's a very difficult question, and
Yes.
but yeah, at the moment, what do you think? Do you think it's possible?
Well, yeah. Well, you see, I sort of invented a way to time travel. Is it possible? Okay. So you see, first, I go very small. So small, in fact, smaller than space-time. So you see,
Okay.
in there, I could go very fast. So I go at super speed, and maybe I'll reach hyperspeed, or maybe is this possible? Is that possible to time travel that way?
I don't know. I think going very small would mean is a very difficult question.
Yes,
How small? And if you were smaller than everything else, how could you exist? Because you're still made of things, aren't you?
you're right.
Um, and yeah, and to think that you could be smaller than space-time, I think that's a very interesting idea. I think space-time is not, as many people think, super 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 tiny until infinity.
You're
It's
right.
it's because of what we know about quantum mechanics. It's
Yes.
actually quantized, so there is a smallest thing. And maybe
Yeah.
if you could go smaller than that, then maybe it's possible. But then my question would be, if you were smaller than the smallest thing in the universe, what would you be made out of?
You're right.
I think that could be a difficult, but maybe, who knows? I mean, it's a very difficult question because, we understand the world now,
Yes.
and we think that people in the future will understand the universe in the same way that we do now. But
You're right.
maybe in the future they will have some amazing ideas and think, no, actually the universe is like this and time travel is possible. So I think it's a very difficult question.
You're
Yeah.
right.
Yeah.
You see, my most interesting part about quantum mechanics is the Schrödinger equation.
Okay. Yeah.
The wave function, getting the wave function is very interesting.
Okay. But which bit of it, what do you find interesting about it?
Well, you see, the wave function describes the particle, right?
Yeah.
Yeah, I already seen the diagram of you see the hydrogen atom's electron. Using the wave function, we can get the hydrogen atom's wave function. I've already seen the picture of that, and it was very amazing. It looked like stars twinkling.
It looked like what? It looked like,
Stars.
yeah, like stars. Oh, like a twinkling star. I see. Yeah. That's a good point. I'm trying to think. You're talking about the electron in the
hydrogen atom.
the electron's wave function
Yes.
in the hydrogen atom.
Yes.
Yeah. Have you seen some videos on YouTube about it?
Oh yes. Yeah, you see. Yeah, I researched some and it was really amazing.
It's amazing. They have all sorts of. I would highly recommend. I think YouTube is a great source of information, and it has amazing animations.
You see, I always use YouTube to research. Well, I'm not sure if I'm that good at reading. Oh, well.
Well, you don't need to be for science. It's fine. I'm not very good at reading either. I'm not very good at all. Yeah, I think if you've seen, I think the idea of a wave function is very difficult because most people think that something, for example, the electron has to be, well, it has to be here or there.
No.
But
No,
it doesn't.
It could be
right?
anywhere. That's
Yeah.
quantum mechanics. It probability rules.
Yeah, exactly. Yeah, very nice. I think that's a good way of saying it.
It was really stars twinkling.
Yeah, I think it's an amazing idea and one that I think we don't really understand fully even now. I think of quantum mechanics in a big way as something that we are very good at calculating solutions, but
Yes.
until we get to a solution, we don't actually know what's going on. There's a very famous expression in quantum mechanics that you're taught very early on in undergraduate physics, which is be quiet and keep calculating.
It was shut up and keep calculating.
I didn't want to say that to you, but yes, it was shut up and keep calculating, right? And
yes.
the idea
I didn't
here,
really get that.
the idea is that once you start understanding quantum mechanics, you basically start asking more and more questions and thinking, this just doesn't make any sense.
How can things be in two places?
Exactly. That it defies all reasoning. But we keep getting really, really accurate answers out of it. And so, it's one of those things in science where if we come up with a solution to something and we're able to find a really accurate solution to it, well, no one really cares if the model itself is true. We only care how good it is at achieving results.
You're right.
And I think quantum mechanics is one of those things where it's incredibly good at receiving and coming up with results and calculations. But
I heard that Einstein.
Yeah.
Okay.
No, go for it.
Okay, thanks. I heard that Einstein hated quantum mechanics. Why?
Well, because of the reason I just gave. He thought that the model doesn't make sense, and he didn't think that one thing could be in two places at the same time. He thought that was impossible. And the other reason is that his theory of special relativity and general relativity, right? Both of those theories don't match up with quantum mechanics.
Yes, how?
So there's an in-between space. Quantum mechanics is the very small, right?
Yes.
And general relativity is the very big.
Yes.
And at the moment, those are our two best models of the universe. But there's this in-between region that's kind of slightly unknown. And within that region, I think there's disagreement between general relativity and quantum mechanics.
Yes.
And that's a really interesting phenomenon. And I think Einstein knew that his theory was not consistent with quantum mechanics.
Yeah.
And as a result of that, he thought that it can't be right. And he wasn't alone. He still isn't alone. One of the most famous physicists around today.
EPR.
Yeah, so EPR, but that's another one. But I was going to say Roger Penrose.
Oh, who is that?
He's a famous mathematician / physicist.
What did he do?
He worked on black holes with Stephen Hawking for a bit, I think. But yeah, he's worked on lots and lots of things, and he thinks that quantum mechanics is also incomplete. That there's something missing. And who knows? Maybe one day when you grow up, you'll work out what it is, and that would be
You're right.
amazing.
You're
But-
right.
But at the moment, I think it's very difficult. Yeah,
Yes.
very, very difficult. Yeah. Do you think? Yeah. No, go for it.
I don't really get the uncertainty theorem. Can you explain it?
The uncertainty principle.
Yes.
Yeah. So the idea here is that we can measure something. So in this case, let's talk about an electron. We can measure an electron's position, for example. And another thing that we can measure is its energy, maybe.
Oh.
Yeah. And those two things are what we call a measurement. Okay. Now, when we measure its energy, actually what we're doing is we're measuring its momentum, because if we know its momentum, then we know its energy. Yeah. As in, if it's got lots of momentum, lots of speed, then it has lots of energy. Yeah. Kinetic energy. Right.
Yes.
And the idea here is that for some strange quantum mechanical reasoning, when we make a measurement of its position, we can't also simultaneously make a measurement of its momentum.
Oh.
Okay. Now that's a really strange thing. Yeah. So if I have an electron whizzing around in a box, let's say, I can tell you by making a measurement, I can tell you that's where it is. Yeah. And in that split moment in time. But once I tell you where it is, I can no longer tell you how fast it's moving.
Oh, you're right.
Okay? And that's a really strange thing. But if you want to think about it, you can think about it in terms of, well, how do I measure an electron? How can I tell where it is? Okay, now there are a couple of ways that you might be able to do that. One nice way of doing it is to just shine a light on it.
Oh.
Now that sounds really simple because an electron is really, really small, but we're going to ignore that for the moment. Let's say, okay, that there's an electron whizzing through the air, okay, and I shine a light on it. So in comes the photon, it touches the electron, the photon bounces back, goes into my eye, okay, I know where it is. Yeah. Now,
Yes.
can I tell you how fast it's moving? Well, I can't, because what I've done by finding out where it is, I've actually sent a photon in and it's collided with this electron.
Yes.
Okay, so now the electron is just collided with a photon, and so maybe it's moving in a different direction now.
Oh, yes.
Yeah? So my measurement of the electron has had an effect on the electron's momentum.
Oh.
And I can't tell you how.
You're right.
So the expression that we usually have is, can you see what I'm writing? If I write something here, can you see that?
Okay.
Can you see what I've written here?
I don't see anything in the chatting box.
Okay, let me show you. I'll write it in the chatting box, okay? So the expression is delta x, delta p, okay, equal to h, roughly, okay? It's not totally right.
Is that h the Planck's constant?
Yeah, it is. Yeah, exactly. Yeah, and it's often h bar over 2, but I can't write that. So it's just delta x delta p is greater than. So what does that say? That says that my measurement error in the position, which is x, the position is x, multiplied by the measurement error in the momentum, p is momentum, yeah, is always greater than h bar over 2. Okay, h bar is Planck's constant divided by 2 pi. Okay.
Okay.
Now, that's all a bit complicated, but all you need to know is that when you make a measurement, it's having an impact on the electron. Yeah. So, for example, you were talking about the wave function of a hydrogen atom. Yeah?
Yes. Yes.
And you have this kind of like crazy shape around the central proton, right? Okay. Now, if I make a measurement, yeah, the wave function immediately changes shape it does what's called collapses. Have you heard that before?
Oh yes, and there's only one curve like this, right?
Exactly. Yeah. So the wave function collapses, and it goes from some funky shape into being a super sharp function.
Ooh.
Yeah.
Yes.
And that means, oh, it's here. It's right here.
Mm.
That's where the electron
Yes.
is, right? So when you make a measurement, you have changed the wave function.
Oh.
Yeah. And this is this strange thing about quantum mechanics where you can impact just by looking at something, you're having an effect on the system.
Yes. It's a mystery, right?
Well, yeah, I think it's a mystery. I don't think it's very well understood. And it's very difficult to understand fully. But yeah, the idea here is that a measurement of something will impact it, which is totally
different. Can you tell me more about? Oops.
Yeah.
I interrupted again.
No, that's fine. That's fine.
Okay. Can you tell me more about quantum mechanics?
Yeah, of course. So that thing is called the Heisenberg uncertainty principle. Yeah.
Ooh. Okay.
Which is a very fancy name.
Yes.
And the difficult thing about quantum mechanics is that there are lots of different interpretations of quantum mechanics, lots of different ways how people explain it. Yeah, so before I was talking about this model, and then it spits out calculations that are really, really good. Yeah.
Oh.
Now, there are a couple of different models, okay? And some of them are different in different ways. That's a confusing thing to say. But you have different interpretations, like the Heisenberg interpretation or the Copenhagen interpretation. Yeah. And these are all, have you heard of those before?
What's this Copenhagen thing?
The Copenhagen interpretation is the one that I've given you.
Oh.
So the idea that your measurement impacts the system. Okay. Now, have you heard of the double slit experiment?
Oh yes. Oh yes.
Yeah.
Well, it fired electrons through two slits, right?
Exactly. Yeah.
And it formed a wave result.
Exactly. Yeah. Exactly. So, and that's a really confusing thing to experience for physicists, I think, at the time. Okay. Let me show you my screen. So, is this your first ever Ringo lesson?
Oh yes, right. Yes, this is my first ever lesson in Ringo.
Okay, that's totally fine. So, this thing that I'm showing you here, can you see that?
Yes.
So this is actually the place where I'm supposed to be writing down everything that you say. Okay.
Oh. Okay.
But because of what you said in your lesson request, I'm not going to do that because we're just having a conversation about physics. Now, if you would like me to correct you or correct your English, I'm very happy to do that.
Okay.
Would you like
I'm
me
more
to...
interested in okay.
Okay, that's fine. So why don't I after the lesson I can go over these three answers to your questions and I'll correct them a little bit. Yeah.
Okay.
Good. I don't think there's a lot to correct. I think your English is very good. How come your English is so good?
Well, I lived in America for about 2 years.
Okay. Amazing. That's very cool.
Thanks.
Okay. So this is my I can't seem to this is my double slit barrier. Okay.
Okay.
Now, electrons are going to come in from the top here. Okay.
Yes.
Now, if I block out this area here, okay, so say it's just one slit, yeah, then what I get is I get a screen here that looks a little bit like this. Let's have a look. Wave function double slit. I can show you the things that I'm looking at. Okay, so can you see all of this? Let me make it a bit smaller. And I'm sorry about the background noise if it's a bit loud. Oops. Okay, so let's have a look at this one here. Okay, can you see that all right?
Yes.
Good. So here's the slit. Okay, here's another slit. Now they're incoming waves. Okay, so the waves are coming in here, and what you get is this really funky overlapping lines. Yeah, and where there's a crest and a trough, and they meet, then they cancel out. Yeah, and you can see these lines here. So for example, here there's a line here. Can you see that?
Yes.
And there's a line here, and there's a line here. And if you look at this line here, there's a line straight down the middle here. Can you see that?
Yes.
Yeah, and because they're overlapping perfectly here, what we get is we get a maximum. Yeah, so this is our measurement wall. Okay, this wall here is our measurement wall. Yeah.
Yes.
Good. Okay, now in the middle there's a really high peak. Okay, lots of waves arriving there. Here we get another high peak, and here we get another one. But in this spot here, for example, yeah, they cancel out perfectly.
Yeah.
So we get no waves there. Okay.
Yes.
So that's the basic of a double slit experiment, and this will happen with waves in the water. This will happen with, and maybe you can see this in school in an experiment. It happens waves in water. It will happen with light waves. Okay, but the strange thing is that it also happens with electrons, but only in specific circumstances. So let me make this a little bit smaller again. Okay.
When we measure it, it becomes like a particle.
Exactly. And when we don't measure it,
it acts like a wave.
Exactly. And that's so weird, isn't it?
Yes.
Yeah.
How come measurement affects this?
Well, this is the idea that I was giving you about how do you measure the electron?
A camera.
A camera, right? So that means that a photon or some piece of light has to bounce off the electron, right?
Yes. Oh,
Okay.
yes.
Yeah. So, and when you make it do that, then you make it decide where it is, don't you?
Oh, yes.
Yeah. So let's have a look at this one here. Okay. So here's your electron gun. That just means electrons are coming out at the end of it. Yeah. Okay. So now for the first example, I want you to say that there's only one slit. Okay.
Okay.
And we're measuring every electron that passes through. And this is kind of like throwing a tennis ball through a gap in a wall. Yeah. In the end, you just expect all the tennis balls to land here, don't you?
Yes.
In a straight line. Okay. Now we're going to open a second slit, but I'm going to measure which slit the electron goes through.
Oh.
Okay. And this is again strangely like you throwing tennis balls at a wall that has two gaps in it. Okay.
Yes.
And your pattern will look something like this one here. Okay. So most of the balls will either land behind this slit or behind this slit. Okay. And very few will manage to get through the middle. Now I'm going to remove the measurement. I don't care which slit the electron goes through. Yeah.
Oh.
I don't mind about that. Okay.
No.
Well, what happens then? Well, then I start to get this strange pattern here. Yeah. Can you see that?
Yes.
Yeah. And that's really, really strange and baffled lots and lots of scientists, and I think still remains to be explained fully. But the idea here is, okay, that when you get the electron, right, it passes through not just one slit, but it actually passes through both. Or I should probably say its wave function passes through both. Okay.
Okay.
Now, when the wave function passes through both slits, it can interfere with itself.
Oh.
Okay. So say, for example, the wave function looks something, maybe this is a bit confusing, but let's say the wave function looks something like, looks something like this. Okay.
Okay.
So it goes through one slit, but it also goes through the other slit.
Okay.
So there's some electron wave function, and it comes across this double slit. Now, once it comes out of the double slit, it creates another wave function. Yeah. And that wave function is going to start interfering with itself. Okay. And then we get that kind of double slit expression that we saw before with that funky looking thing. Yeah.
Yes.
Okay. But what happens if I make a measurement at the slit? Well, if I make a measurement, then the wave function has to collapse, right?
Yes.
And it turns into something that looks like this. So something that looks like this into something that looks like this. Okay.
Just one.
Just one point, yeah. So the electron has to decide which slit it goes through. Okay.
Well,
and now
first,
once it's
keep talking.
So now it's decided what slit it's gone through. Yeah.
Okay.
And
yes.
that means that from then on, its wave function will just come from a single place.
Yes.
Okay? And that's why we get that kind of boring looking double hump. Yeah.
Yes.
Because it either went through this hole or it went through this hole. Yeah.
Yes.
Does that make sense?
Yeah. Yeah. When we measure it, it acts like a particle. But when we don't measure it, it acts like a wave.
Exactly. Yeah. So here, for example, right? Oops. Just trying to spread this out a bit. Yeah. So here's the wave function. Okay.
Yes.
And it goes from being nice and, there are lots of places where it could be, right? In fact, it's in all places at the same time. And now you make a measurement and the wave function collapses and it's the electron is here. Yeah.
Yes.
Good. Okay. And this is what's called the Copenhagen interpretation. Okay.
Ooh.
Can you see?
Yes.
It's a nice fancy name for you. Okay.
Copenhagen.
So this is in 3 dimensions now. Yeah.
Yes.
And I think the Copenhagen is the most popular interpretation of quantum mechanics. Yeah.
Who's this Copenhagen?
I think the person that came up with it was in Copenhagen at the time, or perhaps the group.
Oh.
Yeah. But I'm not totally sure about that.
Okay.
Good. Do you have any questions about that?
No. But it was fun of seeing the wave function collapse.
Yeah, it's cool, isn't it? It's a cool idea.
Yes.
Yeah. So Schrodinger's wave equation tells us what this thing looks like. Yeah. So the picture that I showed you just then was a very simple one. Yeah. So it just looks like a hill, doesn't it? Yeah, like a pointy hill maybe. Okay.
Yes.
And if you have an electron in free space, so that means that there's no obstacles in the way, there's nothing funky going on, right?
Yes.
Then the wave function will look like that. Yeah.
Oh.
And you'll have a little hill that maybe if the electron is moving, then you have this little hill moving through space.
Yes.
And if I make a measurement, then it will most likely be in this exact position here in the middle. But it could be here, and whenever I make the measurement, it decides, okay, it's here. Yeah.
Yes, of course.
Yeah. And Schrodinger's wave equation only tells us what this looks like. Yeah.
Yes.
But remember, the height of this function tells us how probable it is to be there. Yeah. Okay. So here's its position in space.
Yes.
Right. And here's, maybe I can make this a bit bigger and you can get a bigger, better resolution picture. I don't think it is a very good resolution picture, sorry. But the height of it tells you roughly how probable it is to be there. So it's very high here. So it's most probable to be in the middle. Yeah. Okay. And Schrodinger's wave equation tells us what the shape looks like. So if we do something more complicated, like for example, potential well wave function, right? Then maybe it looks something like this. Okay, this is now no longer two-dimensional. Yeah, so they can start to look more crazy, more funky. Yeah.
Yes.
Let's make it 3D. Here we go. Yeah.
Wait,
so it could
when
look,
will it look like more funky?
if it's for example, if it's in a box.
Oh yes.
And it can't escape, then
Yes.
maybe it'll look something like this. Yeah.
Yes.
Okay. And now it has a high probability being here, 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 but it has a very low probability of being on the edge. Can you see that?
Yes.
It's 0 all along. It has a low probability of being right there.
Yes.
Okay.
Yes.
And there, and there, and there, and there, and there. All of the places where it's at 0. Yeah.
Yeah.
It has a 0 probability that you will find an electron there. Okay.
Okay.
Now, when you make a measurement, the wave function will collapse. It will go back into this delta function. Yeah.
Yeah. Yeah.
And that means that it's very likely to be either here, 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 or here. But it could be here, it could be here, it could be here. But it definitely can't be anywhere along the edge. Okay. And it definitely can't be anywhere like this.
Yes.
And that's kind of strange, isn't it?
Yes.
That's really, really strange. And that's the idea behind I mean, these are more complicated ones. Yeah. Quantum eigenstate of a particle in a box. Yeah. So this is in 3 dimensions now.
Okay.
Yeah. So 3-dimensional box, which is even
yes.
more confusing. But Schrodinger's wave equation tells us what these things look like. Yeah.
Yes.
What that looks like. Okay. And then when you
Yes.
make a measurement, it collapses into a delta function. Do you have any questions about that?
Nope.
Yeah. So that's the idea behind quantum mechanics. And you're very young to understand it. It's such it's a very impressive. But the idea
Thanks.
here is that Schrodinger's wave equation tells us where the particle will probably be. Okay. And there are certain regions where it's very probable to be. There's certain positions where it's unlikely to be. Yeah. Okay. And then if you make a measurement, then it has to decide where it is. Okay.
Yes.
Yeah. That's the idea. That is the basic idea behind quantum mechanics, or at least Schrodinger's wave equation. Yeah.
Yes. I guess it's all just probability.
A lot of it is just probability. Yeah. So these wave functions are just probability functions, aren't they? Yeah.
Yes.
Which is, I think, an amazing idea.
Yes. Mr. Brown.
Yes.
What can I call you?
You can call me Isaac. You can call me Isaac.
Okay. Well, you see, Isaac, I sort of want you to show this video because I find it very useful.
Okay.
Okay, wait. It explains a lot about general relativity.
Okay.
Wait, give me some time.
That's all right.
Okay, how do I spell general relativity?
I'll type it here for you.
Type it, thanks. Oh, thanks. G. There it is. Okay, I found it. I'll pass it there.
Great, thank you.
Okay. I'm going to send you the link.
Perfect.
I found this video quite useful. Now in the chatting box. Here's the link.
Oh, amazing. Thank you very much. Quantum gravity. Yeah, this is the new hot stuff in science. Yeah. And it's really, yeah, exactly. So how quantum mechanics ruins Einstein's general relativity. That's the whole idea. This is where the most research is happening at the moment, the most theoretical research, because as I said, we have the large scale thing, Einstein, general relativity, and we have the small scale stuff, right? Heisenberg, Schrödinger, Pauli, Dirac, all of these people, okay? And, you know, because the universe ranges from the very small to the very big, we expect that the two theories should at some point overlap, right?
Yes.
But it turns out they don't. And no one really understands why. So, for example, the Standard Model. Have you heard of that before?
It's about the elementary particles, right?
Exactly. Yeah, and it tries to explain not just the elementary particles, but also all of the elementary forces that exist.
Yes.
Okay. And they have a little entry there in the Standard Model called the graviton. Have you heard of that before?
It's a particle that causes gravity.
Exactly, but they think it does. They've never measured it. They don't know if it's there. They don't know how it works or anything like that. They reckon it might be there, and it has to be there in order to explain all the forces. But they have no evidence of this.
Oh.
Yeah.
I think they can find it in the particle accelerators.
Well, I think they're trying, but I think it's pretty difficult because it's if it does exist, it's very, very small and very difficult to find. Yeah, because it passes through everything, right? But it also interacts with everything that has mass, right? It has an infinite range.
Yes,
and
it does.
all of these things that make it kind of strange. And can it really be a particle? And it's confusing, isn't it?
It's very confusing.
Super confusing. Super confusing. But yeah, I think this is the big issue where you have people coming up with solutions to it. So, for example, string theory is a really nice, neat solution to this. Yeah, where everything is in a little loop and it's all vibrating loops, and I don't really understand it, and very few people do really understand it. But
well, I think it's this. The whole world is made out of one-dimensional vibrating strings. The vibration of the string determines what particle it will be.
Yeah,
I think that's the string theory.
Yeah, it is. It definitely that is it in a nutshell. That is pretty much it. But you know, how does it explain gravity and stuff like that, right? And why is it one-dimensional? And how can we have one dimension in what we experience to be a three-dimensional space?
Yes.
You know, or 4 dimensions if we include time, right? So all of these things are really, really difficult. And I think string theory has the answers to all of it, but it doesn't provide us with any more answers. It doesn't provide us with any solutions, in the way that quantum mechanics does.
Yes.
And unlike quantum mechanics, it cannot be tested at the moment. And that's one of the other big things in science, is that it has to be a verifiable theory, which means that you have to be able to test it. Yeah.
Yes.
Good. Okay. I'm really sorry, but I'm afraid, as much as I've loved this conversation, I'm afraid that's all we have time for.
Okay.
I have another lesson to get to. I hope that was useful. I'm sorry that we didn't do a lot of English, but I hope that was okay with you. Was that okay?
Okay. Yes, it was.
Yeah.
Can we do this again?
Yeah,
sometime
of course.
else?
Just find me on Ringle and we can do it again. Yeah.
Wait, just one more question.
Yeah.
Your name is Isaac Brown, right?
Yeah.
Yeah. It's like Isaac Newton, right?
It is. Yes, it is. Yeah, I was named after him. So I went to, my dad and I went to the same college where he went.
Anyway, bye.
Bye. It was nice to meet you.